Alrighty, let's get this camera centered on this board. And then I think I'll leave the camera right where it is and just move a few boards around. So it's always a little tricky getting started with I guess I'll get back so you can see me chatting. Getting started with a semester, and this video is being made a couple of weeks before our first class. But I have some things in mind, and hopefully this will support what we did in class, what we're about to do in class in a couple of weeks. All right, so we talked about exponents, I believe, in this class, and I just want to refresh some memories about n to the 0 and n to the -2. All right, so n, any number to the 0 power, why is it 1? Well, let's take a look. Let's use a number. 5 times 5 times 5, 5 cubed. You're familiar with that. 125. And if I divide by 5, I get 25, 5 squared. And why? Because really multiplying by 5 and then dividing by 5 is an inverse operation. And we can see that there are 2 more factors of 5 in the numerator from that process. And if we continue that trajectory here, 5 times 5, which is 5 squared, and 5 cubed in the numerator, then we're really looking at the difference of factors. And there's 1 more factor of 5 in the numerator, because 25 divided by 25 is 1, and 1 times 5 is 5. All right, well, here's our 5 to the 0, 5 to the 3, 5 to the 3 in the denominator as well. And so there's no difference. That's what that represents. No difference in factors, and which means you're dividing something by itself. And that's the reason for something to the 0 equaling 1. Okay, and the reason we're talking about it now is so that we can use it, because 0s and 1s are the touchstone of growth in this discipline. And if we have 1 more factor of 5, then we're looking at 5 to 3 minus 4, the rule. The rule is subtraction, and that's 5 to the -1, which is 1 over 5 to the 1. And we don't need to write this exponent, so we won't from now on, but it's understood to be to the power of 1. All right, so that's going to be something that's going to launch our work in exponentials and logarithms. But let's continue on here. So 5 squared, nothing new there. What might be new is what happens when I put a 2 in the denominator. Well, it cancels the squaring. And so what cancels squaring? What undoes squaring? Square rooting. All right, so 5 to the 1/2 is another way of writing the square root of 5. 5 to the 1/3 is another way of saying the cube root of 5. All right, so what do we have in the denominator? Exponential denominators are roots. So right now we have powers and roots. So we take a number, we have powers and roots, which are inverse operations. Okay, it's something that we need to begin to think about. And we've already talked about the minus. The minus you can think of as a reciprocation. Right here we have 5 over 1 to the -1 becomes 1 over 5. It basically reciprocates the base. Those are your 3 rules: reciprocation, powers, and roots. And we want to get good with them. We want to be able to work with them with ease. And to do that, we talk about them every day a little bit. We haven't been talking long, but we're talking about it, and we'll work with it on our worksheets every day. All right, so here's a chance to get started. What would be the best way to do 16 raised to the -3 over 2? Well, I don't think I want to reciprocate it. I don't want to reciprocate it right now. It's easier to talk about powers and roots. Since they're inverses, you get to do whichever one you want first. We'll definitely elaborate upon that in class, but for right now, just planting some seeds. Well, I think you could take the square root of 16 and call it 4, which means you use that operation. And now you've got 4 to the -3, which is 4 cubed. 4 times 4 times 4 is 64. That's a good one to remember. We'll be working with it a lot. And so I would do that next. And so that would get me the number 64, but I still have to deal with that negative sign. And now it would be time to reciprocate 1 over 64. Yeah. So as we go through problems now, you want to get in the habit of pausing the video and trying it yourself. Just give it 5 to 10 seconds worth of thought. And if it doesn't come to you, play the video immediately. I mean, math's a language. We want to treat it as a language. And if you ask me how to say desk in Russian, I could try as hard as I want. I don't think I'm going to get it. So the first stage of learning is following. So give 5 or 10 seconds to try 8 to the negative 2/3. And if all of a sudden you got no thoughts as to how to proceed, just play the video. Keep playing the video. All right, so now we're doing 8 to the negative 2/3. All right, if it's my problem, I'm cube rooting immediately. Cube rooting 8 is 64. I'm sorry, cube rooting 8 is 2. I was thinking of the 2 there for a second. So 2 ways to do it. 8 squared is 64. And that would be still to the negative 1/3. That's a choice. Or you could take the cube root of 8, which is 2, to the negative 2. I think it's far easier to go small than big. All right, so what's 2 to the negative 2? 1 over 4 or 1 over 2 squared. I write it that way. So I'm putting 2 squared in the denominator. Okay. All right. And which is 1/4. Okay, how would you do 1/4 to the 3/2? Pause the video. I just keep going. I definitely, I meant to put a negative. So pause the video again. Okay, what would be the first thing? Well, I think working with integers, easy. Well, integers are fractions too, but whole numbers, whatever, a whole lot easier. So I would definitely reciprocate first. That's 4 to the 3/2. And you can either do 4 cubed, which is 64, and take a square root, or you can take the square root of 4 and cube it. That's my choice. 2 to the 3 gets you 8. All right, so we're up and running. We've got some problems that you can see on a worksheet. And you will tomorrow. I'll make sure those are on a worksheet. When you go to the board, you get a chance to work with your classmates, talk about the problems. And those will be on every test the rest of the semester. So it might take you a minute right now to kind of sort out, oh, let me do this problem. Hopefully it's 5 seconds a few weeks from now. All right, so where do we go from there? Well, turning the board around. I'm also hoping that we talk about order of operations and that we've done some of this work in the first class. If not, it doesn't hurt you to see it now. So this is notation for calculation. F calculation takes numbers, squares them, doubles them, subtracts 7. The G calculation cuts numbers in half, multiplies them by 7, and adds 5. And we're going to actually perform an evaluation right now by dropping in a number. The number 3 goes in place of X, and X means something in Arabic. So 2 times something squared minus 7. What is that something? I'm telling you that X is 3. Now, hopefully we talked about this in class. Squaring is a more difficult operation. Historically came later than doubling. I'm guessing, but I think it's probably true. So we're looking at 2 times 9 minus 7. 18 minus 7 is 11. You didn't have a lining up your equal signs. Then here's another calculation where we're going to drop in a third. So 7/2 times 1/3 plus 5. And I want to get some fraction work in early on. So we've got 7/6. We might have to explain that, unfortunately, for some folks for whatever reason. And then we got to get a common denominator of 5 is 36. So therefore we have 37 over 6. And we have performed an evaluation. We'll be doing those throughout the entire semester. So what does g of x equal 26 stand for? Well, it means that up here, another name for g of x is 7x plus 5. So this is the same thing as saying 7x plus 5. 7x, 7/2 x plus 5, I should have said, equals 26. Then we have to ask ourselves, well, what's the easiest way to do that? And I'm not a fan of do the same thing to both sides. I hope you forget that immediately for me right now in my class. So please, none of this, none of that. If you're going to get up the ladder in this discipline, That's a crutch and it's not helping you in any way, shape, or form. All right, so if I had a number, I could multiply it by 7, divide it by 2, and add 5, and I'd be at the result. The last thing I said was plus 5. So if we evaluate from hard to easy, we solve from easy to hard. So the easiest thing to do, and let me show you why. 7 plus 5 is 12. Correct me if I'm wrong, but I believe 7 is 12 minus 5. Okay, so what's the thought process? Addition of a number on the left can be written as subtraction of that number on the right. Well, I've got addition here. I'm trying to isolate my variable. So I am definitely going to subtract 5, and I can do that in my head. And if you write anything more than that, it's harder for me to correct. Okay, so subtract 5. Now we have a choice. Multiplication by 7 can become division by 7. We can look at that real quick. 7 times 3 equals 21. What's 3? 21 divided by 7. Oh yeah, multiplication on the left, division on the right. Let's look at division. 10 divided by 2 is 5. Division on the left, multiplication on the right, and vice versa. All right, so your easiest way here is to do it in steps. So you can either divide that by 7 or multiply it by 2. Okay, in this case, I'm going to multiply by 2 because usually it's easier to get rid of the division in most equations. So I'm going to multiply by 2, and that means that I have 7x equals 42. I'm going to divide by 7. I get an answer of 6. Now, I didn't fill in everything, and I don't care if you do, because I'm after a thought process here, and I'm all for thinking. All right, that's this class. This class is about getting a hold of the topics that we've got and really grabbing onto them and understanding what to do with them. All right, so we can always check our answers. And if we do, the easiest way to do this would be to divide 2 into 6. 3 times 7, 21. 21 plus 5, 26. And it doesn't hurt to check your work so you don't have any carelessness. Now, I might not have talked about what this means. But what it really means is starting with a number, right? And in this case, the number might have been, what did we just solve for? I forgot. 26, some number here, let's say 20, let's put a 4 in, 14, 19. Let's say we were solving for 19. Well, what would you do? You'd subtract 5, right? You'd subtract 5. If this was some other number, right? Then what would you do? You multiply by 2. That's an Algebra 1 concept for you. That's a new number. You got to double both parts. I hope everybody has seen the distributive property multiplication. 6 plus 8. It's hard to know who's seen what these days with COVID and everything else, but hopefully you can see that that's true. So I'm doubling. And then where was I? Oh, multiplication by 7, division by 7. That's the thought process that we're going to have. And then if I put this number in here, 19, well, let's put a 19 in here. 19 minus 5, 14. 14 divided by 7 is 2. 2 times 2 is 4. So g minus 1 of 19 equals 4. And g of 4, remember what we did up here, g of 4, 2 goes into 4, 2. 2 times 7, 14, plus 5, 19. So up here, g of 2 equals 19. And the inverse is g negative 1 of 19 equals 4. Just some notation. And again, I'm not trying to teach this in one day, just putting it in front of you. You got to learn to be comfortable with being uncomfortable in math. So here's your chance, your first class, to learn to be comfortable being uncomfortable. A lot of math concepts take time to understand and to work with. Just getting it in front of us so we can start that work. All right, so that's board number 1. Out of the way. And hopefully this is not going to be much longer than a 40-minute video, if that. We'll see. Talking to you a little bit at the start. All right, so we spelled this out. Your brain looks at the word log, and I hope it does what? It says, oh, I'm looking for the exponent. I'm looking for the exponent on top of a 4 that gives me 16. And what we do with logs is we rewrite what's in the parentheses in terms of the base. And now I can see that the exponent I put on top of a 4 to get a 16 is a 2. Okay, can we figure out what might I do to a 5 to make that happen? Well, certainly 5 over 1 is going to flip. It's got to have some kind of reciprocation. And I got to turn a 5 into a 125. So what do we have? We have 5 to the what equals 1 over 5 cubed, which is equal to 5 to the negative 3. I wrote a 2, but meant to say 3. I can see my exponent now is negative 3, and that's the answer to this problem. Yeah. And what do I do to take a 9, turn it into a 3? Well, this has nothing to do with multiplication or division. Log, right? What's the brain say? It looks at the base. The word means find the exponent that gets you a 3. Well, I know 9 could be written as 3 squared. And that is the same thing, 3 to the 1. And our rules of exponents, 3 to the 2x equals 1. So therefore, x equals a half. And from our class today, I hope you know that a half is an operation. And the square root of 9 is 3. Right? If you didn't know that before you watched the video, and you still might not know it, it's something we want to talk about because we eventually have to know it in order to work with these problems. But no worries, because it's just day one. And I want to throw a little conceptualization at you. I want to talk a little bit about squares, because I think that this whole discipline really evolved from the relationships that we see in rectangles. So much of what we do in math is still based on that. So I've done a couple of number crunches over here. 0 gets you 0, 0 squared. Of course, 0 squared is a pretty small square. It's even smaller than that square. It's even smaller than that square. It's even smaller than that square. In other words, it doesn't seem like it has any area. But next one is 1v1. I could see that as a 1v1. And then maybe a 2v2. Oh, a 2v2 has 4 square units of area. A 3v3 has 9 square units of area, so on and so forth. And we could plot some of those values. No area with side length, so the x-axis now is side length. And the y-axis represents area. And there's some famous ones. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Kind of looks like that on the right. And I suppose we could do -1 times -1. It's hard to think of a side length as being negative, but we need negative numbers to work with in math. And we get the same symmetry. You know, a negative times a negative is a positive. I hope you learned that in pre-algebra and earlier work. All right, but a deeper dive into quadratics, fancy name for rectangles, quad Latin for 4. I just decided to get a little bit bigger and cube it. Not much change there. You know, we define change as one output minus another divided by one input minus the other. You know, and there's really not much change there. It's pretty flat here. Pretty flat right there. Oh yeah, it's flat there. Yeah. And then 1.001 squared. Now, you don't need a calculator because there's some patterns here. 1.002001. Whereas if I square 2.001, I get 4.004001. And if I did a 3, I get, oh, I did more decimals this time. 1, 2, 3, 4, 5. I get 9.12346, right? 001. And, you know, 4 gets me 0.1. See, I got 4 decimals. 1, 2, 3, 8. 1, 2, 3. Yeah. So you might want to pause the video and look at those. See if you see any patterns. When we describe numbers, There's usually two things I want to hear from you first. Is it positive or negative? You know, if it's neither, it's zero, obviously, but is the number positive or negative? Is it big or small? Well, 3 decimal places. 3 decimal places, 001. 001, 001. 001, 001. 001. 0001. 0001. Well, I got news for you. This number here could have been written as 4 plus 0.004 plus 0.000001. That number is very small. It's so small that it's insignificant. So we can get rid of it and really look at how things are changing. Okay, so this isn't changing much at all. Oh, no area there, it's hard to change it. Well, this number starts with a 1, that ends with a 2. This number starts with a 2, it ends with a 4. This number starts with a 3, it ends with a 6. I bet you can guess what this one ends with. Oh yeah. So if we were to perform y2 minus y1 over x2 minus x1, let's just take care of the ones here because I can divide this by 0.001 and it looks like it goes in twice. In other words, at 1, I'm kind of going up at 2 to 1. At 2, I'm kind of going up at 4 to 1. At 9, I'm going up at 3 to 1. Because these are continuous functions. And I just wanted to plant a little seed there. All right, so now where are we? This board is done. We're almost done. So, the things we've talked about, I hope that we established in our very first day. Maybe not, because you got to have introductions, you got to know your classmates and everything, but if not, then this might be the first time you're hearing this. Hopefully not. Let me put the camera down a little bit more. All right. So order of operations, hard to easy. Using and making zeros and ones. You're going to get a little practice with that on the other side of this board in a moment. Input outputs, X to Y. You know, if we're going to study the world and relationships, then, you know, global warming to temperature, you know, there's all kinds of correlations that need studying. And boy, do we need to study some of them soon. Letter X comes from, is Arabic. It means the word something. So if I said 2x plus 3 equals 21, then 2 times something plus 3 equals 21, and you find it. And we can do that quickly. 18 divided by 2 is 9, right? Inverse operations, we just talked about that before. And so yes, order of operations and solving equations involves inverse operations. And we're going to do a lot of solving of equations. I like to think of graphing as numerical mapping. And so I'm going to use that term during the course of the semester. Evaluating, we talked about that with the f of x and g of x commentary a little earlier. And exponential rules. So we've got some stuff that you're going to see tomorrow on a worksheet. Might introduce something else for 5 minutes, and then you go to the board and you begin the work of getting to know what you're looking at. All right, so with that in mind, let's look at the similarity. Oh, yes. And the most important one, conversion. That's what we're going to practice right now. And you know, what kind of knowledge do you have of the functions that we're studying? I wouldn't think a whole lot. Oh, I don't know what your algebra, pre-algebra experience was, but got to start somewhere. So let's start talking about these things. So this is a linear function. Y, it makes a line. You're drawing a line on a graph. Okay, we just talked about squaring. So this is, you know, quadratic, rectangular relationship. I wish I had gone back here and done square roots, right? Because squaring, right? The squaring process is 0, 0, just on the positive side of things, 1, 1, 2, 4, 3, 9. But I could also come up with a calculation that goes 0, 0, 1, 1, 4, 2, 9, 3, 16, 4, etc. And these could all be plus or minus, right? This could be, we're still going to get those. Whereas we generally think of square rooting, which is what this is all about. Square rooting, that's a square root, by the way. Terminology comes from things, right? Geometric interpretation here. And that's a distance, really. That's a distance. So we only take the positive numbers and then work with them. But that's not something you have to worry about too much at the moment. But how would we, and if we look at this graph, squaring looks like that, square rooting looks like that. It's the inverse, switching the x's and the y's. So each of these graphs has their kind of look to them. And by the look of the graph, you can kind of determine what calculations are involved. So what are the equations here? Well, the conversion, principles of conversion, subtraction and the operational division. Those are the hallmarks of the conversion process. Subtraction, get rid of what you don't want, bring in what you do. Divide out what you don't want, bring in what you need. Subtraction, get rid of what you don't want, bring in what you do want. Division, operational division, get rid of what doesn't work, bring in what does work. All right, so how do I turn a 5 into an 8? Well, a 5 is not an 8, so I get rid of it. I subtract it out of the problem, and I bring in what I want. Okay, this is to the first power. What do? I use my second x. I put my second x in there, and I get 11 minus 5 to the first power, which happens to be 6. 6 plus 8 does not equal 27. I get rid of what I don't want. I bring in what I do want. Now, what plus 8 is 27? 19. Okay. Well, that's the process. Let's do it for the quadratic. Quadratic, and I'll put this a little higher up. Do it again quickly. Write a little smaller. So 19 over, I think I'll keep it 11 minus 5 to the first power right now. Times x minus 5 plus 8 goes through those 2 points and is linear. Okay, 5, 8. X minus 5 squared plus 8. That's a quadratic relationship. Okay, if you put a 5 in, 5 minus 5 gets you 0. And I don't know if you remember, but we had a square, and 0 was a very small. In fact, there was no area. And it's the smallest square that I can draw for area. The smallest. And this is at a minimum, smallest place. So I want that number to act like the 0. So I get a minimum area. Just throwing in a little conceptual context. All right. So now I drop in an 11, and I get 11 minus 5 squared. That's what I get. I drop in an 11 here, I get 36 plus 8. And correct me if I'm wrong, I don't think that's 27. So what do? I get rid of it through division. I get rid of that change that doesn't work, and I bring in the change that does. There it is. Square roots. Square roots go from the area to the side length. The side length to area seems to accelerate. Area to side length, the inverse of that. So what do? Square root of x minus 5. Oh, again, square root. Well, that's a distance. Well, guess what? I can make that square root smaller. I can make that square root smaller. In fact, I can make it go to 0. Right? And I guess this is another minimum. So if I put a 5 in, that's the smallest this thing's going to get. And I want to get from 5 to, I'm going to put an 11 in. And if I put an 11 in, I think I get the square root of 6. that's not square root of 6 plus 8. Correct me if I'm wrong. Square root of 6 plus 8, I don't think equals 19, equals 27. I wanted, yeah, 27. No, it doesn't work. So I get rid of it through division and I bring in what does work. I don't know if we talked about absolute value or not, but let's think of this as a number line, just the x-axis, and let's make it go in two directions. Absolute value really measures distance from 0. So let's call that 0, distance from 0, and distance can't be negative. So even if I'm at -2, I'm really 2 steps from 0. If I'm over here at 7, I'm 7 steps from 0. So what an absolute value does, I'll just draw y equals x here for a second. My horizontals and verticals are equal. I go over x, I go up that amount for y. Over x, that amount for y. Right? Back, -1, down -1, -2, minus. In other words, they're equal. So what happens when I slap an absolute value on y equals x? What happens when I slap that? Well, all those negative distances become positive. And I get a V-shaped graph. All right, so what do I want? Again, a minimum. Where does it occur? 5. What's the smallest distance you can travel from 0? Is 0. So I want to make a 5 into a 0. I guess I'm x minus 5 again. But it's an absolute value measuring from now, the number 5. So I'm on a number line measuring from 5. How far did I go? How far did I go? And I know 5 matches up with an 8. So I got to get that correlation. And now I put an 11 in. And so I really have the absolute value of 11 minus 5, which is 6. Again, 6 plus 8 does not equal 27. So we got to get rid of that 6 through division and bring in the 19. And that pretty much ends our discussion for this video. I will change this to 11 minus 5 is 6. 11 minus 5 squared is 36. 11 minus 5 square root is the square root of 6. And 19 over absolute value, 11 minus 5 is 6. I think there's a lot of similarity there. If you get it in one place, you get it in them all. Now, I don't expect that to mean a whole lot to you yet. We got to get some mechanics down before we can really get into more discussions about the geometry behind all these things and their implications going forward. But for now, mechanics will suffice. See you in class tomorrow, and we'll start where we just left off. Ta-da.